A vector space is a foundational idea in mathematics and engineering, describing a collection of objects called vectors and rules for combining and scaling them. While vector often suggests physical arrows, the concept of a vector space is much broader. Almost anything that behaves like a list of quantities that can be added and multiplied by numbers can be considered a vector in a vector space. This idea, though abstract, forms the backbone of physics, computer graphics, machine learning, and signal processing. Understanding vector spaces provides a flexible language for describing and analyzing patterns. What is a vector? In everyday math, a vector is often an arrow with direction and length. For example, a vector tells us a plane's heading and speed. But in a vector space, a vector doesn't have to be a physical arrow. It can be a list of numbers. It can also be a point on a grid, a sound wave, a temperature distribution, or a probability model. Even words represented as embeddings in AI systems are vectors. The key is that you can add one vector to another, and you can multiply a vector by a number called a scalar. If both operations follow certain consistency rules, the collection of vectors forms a vector space. Imagine a flat sheet of paper. Any point can be described with two numbers, like how far right and up it is. Each point is a vector. Adding two vectors gives another vector still on the paper. Multiplying a vector by a number keeps it on the paper. This sheet is a two-dimensional vector space. Now, consider a room. Any position can be described using three numbers: left/right, forward/back, and up/down. This creates a three-dimensional vector space. But vector spaces aren't limited to dimensions we can see. You can have four-dimensional, 10-dimensional, or even infinitely many dimensions. Higher dimensional spaces appear in many real applications. Why vector spaces matter? Vector spaces are powerful because they allow us to analyze complex problems using consistent, structured rules. For example, in computer graphics, every 3D model is a collection of points in a vector space. Lighting, shading, motion, and rotation all rely on vector operations. In machine learning, data is turned into high-dimensional vectors. A picture might be a vector with thousands of numbers. A word can be a vector capturing meaning. In physics, forces, velocities, and fields are vectors. Their behavior follows vector addition and scaling. In audio and signal processing, sounds are vectors of wave shapes. Filtering, compression, and equalizers rely on vector space operations. Vector spaces provide a mathematical coordinate system for understanding relationships. The dimension of a vector space is the smallest number of independent directions needed to describe every vector. On paper, you need two directions. In a room, you need three. Consider digital photographs. A black and white image with 1,000 pixels has a value at each pixel. So 1,000 numbers describe the image, meaning it exists in a 1,000-dimensional vector space. We can't visualize this space, but the math works the same as with arrows in a room. The power of vector spaces is that the same rules apply, whether the dimension is 2, 3, 100, or a million. A basis is a set of vectors that act like fundamental directions. Any vector can be expressed as a combination of these directions. Think of compass points. North and east form the basis for navigating a map. Up, forward, and sideways form a basis for navigating a room. In higher dimensional spaces, basis vectors are not physical directions, but they define the space's coordinate system. Choosing a good basis can reveal hidden patterns. This is central to methods like principal component analysis in machine learning. Sometimes, a smaller space lives inside a larger vector space. A flat sheet of paper in a room is a two-dimensional subspace within a three-dimensional space. Subspaces are important because many real-world problems focus on only certain aspects, simplifying analysis. A vector space is a collection of vectors that can be added and scaled according to simple rules. These vectors don't need to be physical arrows. They can be data points, signals, shapes, or patterns. The beauty of vector spaces is they provide a common framework to describe and analyze many systems across science and technology. Whether working with aircraft motion, digital images, neural networks, or sound waves, the underlying mathematics is the same. In short, a vector space is a structured world where objects combine and scale, allowing us to understand relationships, simplify complexity, and solve real-world problems.